This is a video lecture teaching students how to use the electronic device known as demultiplexers. In an electronic circuit, one of the more commonly used devices is called the multiplexer, also known as a mux. A multiplexer is a device that selects an input signal from multiple sources and results in a single output based on the select bit representation provided. Here we have a 4x1 multiplexer. 4x1 implies that there are 4 inputs corresponding to one output. The output is determined based on what the select bits are. Based on the select bits, the specified binary representation of the select bits will provide that data input signal to go to the specified output signal. For example, if you'd like to represent D2 in this diagram to go to F, you would need C1 to be equal to 1 and C0 to be equal to 0, because C1 and C0 would equal 1, 0, which is the binary representation of the decimal number 2. Thus, F would get the input signal D2. Now, a demultiplexer works the opposite way. You'll have one specified input signal, and the output that receives this input signal is determined by the select bits. For example, you have an input X, according to here, and if your select bit is 0, then X will go to output signal 0. However, if select bit was 1, then X would go to output signal 1. The select bit determines which output gets the specified input, unlike a multiplexer, where the select bits determine which input goes to the specified output. The inner workings of a demultiplexer are very similar to those of a decoder. For example, you can see that you have one input X and it splits up into its 4 respective values based on the select bits. However, a decoder works as such. If you have an n number of inputs, the decoder will represent those inputs in their 2 to the n binary representation. What that means is if you have 2 inputs, the decoder will have your outputs being 2 to the n outputs. In this case, n is 2. So 2 squared is 4. With 2 inputs, you will have 4 outputs. However, the significant difference between a demux and a decoder, while they have all these other similarities, is the fact that a demux always has a write enable. However, a decoder doesn't necessarily need to have that configuration. This differentiates a demux from a decoder. Now that we've learned about demuxes and how they're different from multiplexers, let's go on to an example. Our example is that we're going to implement a 3x8 decoder using only 2 1x4 demultiplexers. This is possible, and here's how we'll do it. So what the example problem is intending for us to do is to implement a 3x8 decoder using 2 1x4 demultiplexer designs as we've explained before. So, how a 3x8 decoder works is that you will have 3 inputs corresponding to 2 to the 3rd outputs. As we explained before, for any n amount of inputs in a decoder, you will have 2 to the n outputs, as that is the total number of binary combinations with the respective inputs. So let's call these inputs x, y, and z. With n equals 3, you know that you're going to have 2 cubed equals 8 outputs. This means your outputs are going to be 0, 1, 2, 3, 4, 5, 6, and 7, respectively. Now let's use this 3x8 decoder to implement a function f of x, y, z is equal to the sum of minterms 1, 2, 4, and 6. What this means is that sum of minterms 1, 2, 4, and 6 is going to be equal to x naught, y naught, z plus x naught, y, z naught plus x, y naught, z naught plus x, y, z naught. We want to implement this using our decoder design. So first, doing that, we will have, as said before, our respective outputs 0, 1, 2, 3, 4, 5, 6, and 7. The sum of them essentially means that we need these inputs to connect to an OR gate, which will then output to F. So you would have inputs 1, 2, 4, and 6 connect to the specified output. And thus you would have implemented the function. Now, instead of using a 3x8 decoder, Let's implement this using two 1x4 demultiplexers. So as explained in the problem, with two 1x4 demultiplexers, you're going to have one input and four outputs. Now, we have to see how we'll be able to have these outputs with their select bits included all connect to be just like the 3x8 decoder. Let's look at the combinations of x, y, and z. You'll notice that with x and with x naught, they have the same respective combinations of y and z, which will be y naught, z naught, y naught, z, y, z naught, and yz. So with x being able to combine with all four of these combinations of y and z, and x not being able to combine with the same ones, you can have x naught being the input for the first to represent the first four outputs, and then you can have x being the input for the second to represent the last four outputs. How does this make sense? So let's apply y and z as our select bits, since there are four combinations of those that we can use for our combinations in the demultiplexer. When you have y and z both being 0, that will mean that you're going to have the output being the binary representation of 0, as x naught is also 0. 0, 0, 0 is the binary rep of the number 0. Now, it works for this because x naught is going to make sure that the first bit is going to be 0, and the yz combination just runs through the four combinations of the 3 bits once x bit is fixed as 0. With the second demux, it fixes the x bit as 1. And that means with the yz combinations, you can get the last four numbers, which is going to be 4, 1, 0, 0, 5, 1, 0, 1, 6, 1, 1, 0, and 7, 1, 1, 1. So, as requested before, in our function, we want to have f of x, y, z being sum of minterms 1, 2, 4, and 6. Now, what we have here is our outputs 1, 2, 3, 4, 5, 6, and 7. So we can take these minterms and combine them all the same way we did with the decoder, as we now have the specified outputs that we require for the function. So we will take the specified inputs, connect them all to an OR gate, as we want to sum the terms, and we will have these OR gates all correspond to the output f. Thus, we have implemented the function using two 1x4 demultiplexers in order to represent one 3x8 decoder. We have discussed demultiplexers and multiplexers. As shown in the leftmost image, we discussed how a 4x1 multiplexer works, with 4 data input signals corresponding to one output signal. That is, the output signal being determined by the select bits determining which data input signal goes to the output signal. We also discussed demultiplexers, where you will have one specified input signal, and the output signal that receives said input signal is determined by the select bits. Running through example problems, we see how a demux is essentially the reverse of a mux, and we also discussed how a demux is very, very similar to a decoder, as we have shown in our example where we implemented a decoder using a demux. However, keep in mind that the strong difference between a demux and a decoder is the fact that demuxes always have a write enabled, but decoders don't necessarily have that. Thus, you see, demuxes are essentially the reverse of muxes, where you have an input corresponding to multiple outputs, as opposed to multiple inputs corresponding to one output. This concludes our lecture.